In the last video, I briefly mentioned that stacks and queues are the two sides of a coin, where a stack is last in, first out, and a queue is first in, first out. Both have multiple elements that you can add or remove one at a time, but the order of removing elements is different. A queue works like a queue in real life. Think of a line of people waiting outside a restaurant to get in. The person who comes in first will get served first, and new people coming into the queue will have to stand at the back of the line and wait until it's their turn to get in. Now let's turn these people into queue elements. NQ is when an element is added to a queue, just like when a new person stands at the back of the line. And DQ is when an element at the front comes out of the queue. These are the two main operations of QADT, NQ and DQ. Now that you know the two main operations, aka the interface of QADT, let's think about how to implement them. Just to make it easier, let's assume we have a max size for the queue. How would we implement NQ and DQ? Each time we NQ an element, we add that element to the array. If we want to DQ, we will have to remove the first element, since that was the first one in. That means we have to shift all the elements in the array to fill in the empty spot. So this will be an O of n operation. So that means NQ would be O of 1, but DQ would be O of n. Let's think of a way where we can still use an array to implement the queue, but also NQ and DQ in constant time. Can you think of a strategy? Here's a hint. We can form a circle with the array elements and NQ at the rear and DQ from the front. In that case, we won't have to shift all the elements. Here's another hint. If we want to implement this circular array, we need to keep track of the array index of the front and the rear. So we need them in the queue structure. And of course, we will also have to include the max size as well. As you can see here, as long as we keep track of the front and rear index, we can keep on enqueuing and dequeuing without moving or copying the elements. If we reach the last index of the array and we need to update the front or the rear index, we can just restart it to 0 and just keep going. You should try implementing this yourself as an assignment. Okay, so we were able to get NQ and DQ in O of 1, but we still haven't solved the max size issue. We can definitely use dynamic arrays, but that would increase the complexity. So let's try another data structure, shall we? What about linked lists? How would we implement using that? Okay, simple implementation. If we DQ, we'll remove the head. And if we NQ, we'll add a new node to the back of the linked list. From our previous lesson, we know removing the head would be an O of 1 operation, and adding a new node to the back would be an O of n operation because you have to traverse all the way to the last node. However, we also talked about having two pointers for our linked list in our previous lesson. Hence, we can define our queue like this. The pointer to the head of the linked list is called front, and the pointer to the end of the linked list is called back. Now we have two pointers. So for DQ, we can do the same thing we did before using the front pointer, and then for NQ, we can use the back pointer to add a new node without needing to traverse the whole linked list to get to the end. Conceptually, this is pretty simple because we learned about this trick when we implemented the list ADT. Let's see how we can implement it with code. We will first need a node structure that has a value and a pointer to the next node. And the queue structure will have a pointer to the front node and the back node so that we can NQ and DQ in constant time. Great, let's go and implement NQ. The function needs to take in the queue that we'll be adding the new node to. And it also needs to take in x, which is the value that's going to be added. The first thing we need to do is to make a node out of x. So first, we will make a node. Let's call it new node. And then set the value of the node to x. Now that we've made the node, we just need to add it to the back of the list. So we have a pointer to the last node in back. So we can just access the back by saying q.back. And then we will add the new node by setting the next of the q.back to the next node. And then we need to set q.back to the new node, so that if we call the enqueue function again, it will keep on adding to the back. Okay, so far so good, but there's one more thing we need to do. What if the queue is empty and we are enqueuing the first node? Whether the queue is empty or not, we will still need to create a new node. So we'll put an if statement right here, right after creating the new node. And if the queue is empty, front and back would be null. So if the front is null, we want to set new node as a front. And then we'll put the normal case after the else statement. Make sure you keep the part where you set the new node as queue.back outside the else statement, because we'll still need to run that line, even if the queue only has one node. So if we add a new node to an empty queue, new node will be assigned as both the front and back. Okay, now let's write the dequeue function. We only need to pass in the queue because we'll always take out the front. And at the end of the function, we will return the dequeued value. Before we write anything, we first need to check if the queue is empty. And if it is, we will handle the underflow error instead of trying to access things that don't exist and causing problems. So we will write the main code here after the else statement. We have to return the dequeued value at the end of the function. So before we disconnect the front node, we will store its value in a variable r and return that. Then we can set the second node as front so that we can detach and free the first node. Okay, so that was enqueue and dequeue. Let's write two more operations, peek and isEmpty. Peek will return the value of front without removing it. So first, we will check that the front is not null and then return the value. And isEmpty is going to check whether the queue is empty or not, so we'll return the Boolean value of front equals null. Right now, the queue is not empty, so it will return false. Awesome, so we were able to apply what we learned in the list ADT to implement the queue ADT using a modified linked list, where we have a pointer on both the front node and the back node. All right, you must be tired now, but I'm going to leave you with one question to think of. What if we change the interface of the queue? Instead of just being able to enqueue from the back and dequeue from the front, what if you can enqueue from both sides and dequeue from both sides as well? We call this a double-ended queue, or DEQ for short. I'll give you a hint. You'll need to modify your node structure for this, a node augmentation strategy. Think about it. All right, I'll see you then.